Let's understand apparent weight. What is apparent weight? In simple terms, you can say that is apparent weight is, suppose you have to find the apparent weight of a body, you put a weighing balance underneath this body, and whatsoever reading is shown in the weighing balance, that is the apparent weight of the body. So now we have three things. One is mass of the body, the second is weight of the body, and third is apparent weight of the body. Let's talk about first mass of the body. Mass is content of the matter. Unit is kilogram, gram, milligram and all those things. Kilogram is SI unit of mass. So mass is content of matter. If we have a body of 5 kg mass on earth, if we take it on the surface of moon, it will still remain as 5 kg. Even if we take 1000 km above the surface of earth, it will still remain 5 kg. If we take this body of 5 kg mass on the surface of Jupiter, then also this will remain as 5 kg only. So now coming to weight. Weight is m into g. Mass of the body into g is acceleration due to gravity of that planet. For earth, g is acceleration due to gravity is 9.81 meter per second square. If we go to moon, the moon has a acceleration due to gravity on its surface is 9.81 divided by 6 meter per second square. So what's the weight over here? A body has some weight over here. On surface of moon, it becomes 1/6, it becomes the weight. So weight is, when we say weight is equal to m into g, so once the value of g changes, then certainly the weight will also change. The weight can change if the g changes. Acceleration due to gravity, it changes. The g changes with height also. If you go to the other planet also, then also the g will change. So the weight, that can change. Mass is fixed. It is content of the matter of the body. Now coming to apparent weight. Apparent weight is something that is, if we have to find the apparent weight of a body, just put a weighing balance underneath the body and you can find that is what is the apparent weight. Let us understand apparent weight with the help of a weighing balance. Over here, I have drawn a weighing balance. This is, you can say, mechanical weighing balance. This is not a digital weighing balance. So this is a top view of weighing balance. And over here is all the masses, all the weights or so, that is in kgs it has been shown. I'll come to this, that is why we say that is weight in kgs or so. We'll come to that. Over here, when a person stands, then obviously the needle moves. This needle moves. This is a mechanical weighing balance. Suppose it has moved to 50 and over here all the readings it is given as, that is, this is in kg. It says that is unit is kg. So we say that is my weight is 50 kg. As a layman, we can say that is the weight is 50 kg, his or her weight is 50 kg, 60 kg or so on. But being a student of physics, this is, we say that the weight of a person is so many Newton, because weight is m into g, this is force. Unit of force is Newton. It is generally when the person says my weight is 50 kg, it is primarily he or she what says is that is his or her mass is 50 kg and the weight is going to be 50 into g. If we take g as 10 meter per second square, so this is going to be 50 into 10, that is 500 Newton, that is actually the weight. But if on the weighing balance it is shown that is your weight is 500 Newton or so, then certainly for such companies it will be very difficult to push their sales or even to make even a single sale. Let's understand how the weighing balance works or how we take the reading on a weighing balance. Let's say this person is a 50 kg, this is a side view, this is a person, 50 kg person, this is the best I could draw. He is standing, he or she is standing on a weighing balance. This is, suppose we are looking for front. Let's draw the free body diagram for this whole thing, what is happening over here. Over here, this is a 50 kg person. So earth is going to pull it down with a force m into g, taking g as 10 meter per second square. As we said earlier, that is for the only for the ease of calculations, we have taken g as 10 meter per second square. Otherwise, you have to take g as 9.81 meter per second square. So we have separated. First is free body diagram method. As first is slightly we have isolated the body. We have created some space so that we can draw the forces. Then earth says I'm going to pull it down with a force of 500 Newton. This person through his feet, this person through his feet is going to apply a force F1 onto this weighing balance. So this is once again a weighing balance WB. So this applies, this pushes this weighing balance down, this weighing balance pushes down. F1, F1. If we find any F1, so our job is done, that is that we can find what is the reading like. Now this person, after some, let's say as soon as the person stands, generally we see is that is this needle goes here and there and finally it settles at one reading. Once it settles, then certainly this person is neither moving up nor moving down, and this person is stationary, this is not accelerating, this is acceleration is equal to 0. When the acceleration is equal to 0, we know that is resultant force is equal to mass into acceleration. It means the resultant force onto this should be equal to 0. When it is finally balanced, it is not moving, it means F1 is equal to 500 Newton. That is, resultant force is equal to 0, it means F1 is equal to 500 Newton. Now what this weighing balance person does is, the needle has moved to some value. What's the value it has moved? The person says that is F1 is 500 Newton, reading is going to be F1 by G divided by G, that is, if we take is 10, so the reading is 50 kg, and we say, our layman says that is my weight is 50 kg. A student of physics says that is my weight is 500 Newton, let's say in the class of physics. So this is how the weighing balance works. The person stands on the weighing balance, we draw the free body diagram, 500 Newton is downwards, F1 is upwards, F1 is on the weighing balance. Our purpose is, our aim is to find the value of F1. This is not accelerating, so F1 is equal to 500 Newton, so the reading is 500 Newton. But now what the manufacturer does is, he divides the 500 Newton, whatsoever the reading is in Newton, he divides it by 10, 500 by 10, that is by G, he divides it and puts the value over here, that is 50 kg, your weight is 50 kg. This is how the weighing balance works. Now let's say the same person is in the lift, and this lift is going up with 2 meter per second square upwards. Now we want to see, that is, what is the apparent weight now, that is, what is the reading which is going to be shown by the weighing balance now. Weight is constant, weight of this person is 50 into G, G is 10 meter per second square, weight is 500 Newton, there is no change in that. But the reading of weighing balance, it may change. Let's see, that is how it changes, and whatsoever changes, whatsoever the reading is shown by weighing balance, we will say that is the apparent weight. Over here, the lift is going up with the acceleration of 2 meter per second square, and there is a person on the ground, he is our observer, and he says this is a glass lift, this is going up with 2 meter per second square. So obviously the person is also going with 2 meter per second square in the upward direction. So the equation for this, when this person is going up with, so when this person is going with 2 meter per second square in the upward direction, so the net force, it has to be in the upward direction. F is equal to ma, resultant force in this case is not equal to 0 now. It is net force in the upward direction. It is accelerating 2 meter per second square. So now for this free body, the equation is going to be F1 is upwards, upward forces minus downward forces. This is the net force. When we apply F is equal to ma, resultant force is equal to mass into acceleration. Acceleration is upwards, net force it has to be upwards, so we say upward forces minus downward forces. So that's why we say F1 minus 500 is the resultant force, mass is 50 kg into acceleration is 2. So this comes out to be, F1 comes out to be 500 plus 100, that is 600 Newton. Now what the manufacturer does, he divides this value by the value of G. So the reading is going to be 600 divided by 10, that is 60 kg is going to be reading in this case. And this is the apparent weight. His actual weight was, let's say 500 Newton, or in terms of kg if we say, that is the reading, actual reading it was 50 kg, but now the reading has come out to be 60 kg. Now instead of this lift accelerating up, suppose it is accelerating down. It is going down with 2 meter per second square. Suppose from the 10th floor, we are going to the, let's say, ground floor. So obviously initially it accelerates, then moves to the constant velocity, then brakes they are applied, and it halts at ground floor. So this is accelerating in the downward direction, and suppose it is going down with 2 meter per second square. We are interested, that is now what is going to the reading in weighing balance, that is what is going to be apparent weight. All the diagrams, the free body diagram remains same. It is only the last F is equal to ma. There is a change in this because the resultant force is going to be changed, because the acceleration has changed. If this is the whole thing is going with 2 meter per second square, it means this person is also going with 2 meter per second square. So equation for this is, because this is accelerating downwards, so it means net force, it has to be downwards. It means downward forces minus upward forces. So we say 500 minus F1, that is the resultant force, net force, unbalanced force on this body. Our aim is to find the value of F1. As soon as we find the value of F1, the reading is known. So 500 minus F1, this net force, is equal to mass is 50, acceleration is 2 meter per second square, this is 100. So F1 is equal to 500 minus 100. So F1 is equal to 400 Newton. Now the manufacturer does is, he divides this value by the value of G and says your weight is 40 kg. So apparent weight, it has changed. So what we say in layman's term is, when the person was stationary, his weight was 50 kg. When the lift is accelerating up with 2 meter per second square, his apparent weight increases to 60 kg. When the lift is accelerating in the downward direction with 2 meter per second square, he feels lighter and the apparent weight comes out to be 40 kg. Through our experience, we know that is, even if our eyes they are closed, we are in a lift and it has just started accelerating. Through this acceleration experience, we know that is whether the lift is moving up or moving down by the feeling it generates. Generally, the students, they have a misconception, that is, if the lift is going up, the apparent weight increases, and if the lift is going down, apparent weight decreases. This may or may not be the case. Let's see how. Let's say this lift is going up with 3 meter per second. Now we say I have written 3 meter per second. There is no acceleration, this is moving with a constant velocity. If this is moving with a constant velocity, it means acceleration is equal to 0. So the equation is going to be, even if we say it is moving up and we wish to say F1 minus 500 is the resultant force, mass is 50 kg, but acceleration is equal to 0 because the velocity, this is velocity, there is no change of velocity, it means acceleration is equal to 0. Whether the body is moving up or whether the body is moving down, this lift is going down. If it is going up or down with a constant velocity, it means acceleration is equal to 0. If acceleration is equal to 0, then this is acceleration is equal to 0. So F1 is going to be 500 Newton only, and the reading is going to be 500 divided by G, that is 50 kg only, whether the lift is going up or coming down. So what we have to understand is, if the lift is accelerating up, then the apparent weight of the body will increase. If the lift is accelerating down, then the apparent weight of the body will decrease. But it is not the case that is all the time lift is accelerating only and it is not retarding. Suppose we have to go to the from ground floor and we have to go to a 10th floor. So initially, generally what happens is, this lift is initially at a velocity 0. It will accelerate up, moves with a constant velocity, and then as soon as the 10th floor is coming, the brakes they are applied. So from here at the last part, there is a retardation. The same thing happens when we are coming down in lift. Initially it accelerates, moves with a constant velocity, and then as our destination comes, the brakes they are applied, that is we are retarding, the lift is retarding. So now let's understand how the apparent weight changes when the lift is retarding. Suppose this lift is going up and it is retarding this way with 2 meter per second square. Either you say it is retarding 2 meter per second square this way, or it is accelerating minus 2 meter per second square this way, is one and the same thing. Acceleration is equal to minus of retardation, or retardation is minus of acceleration. So this lift is retarding this way, that is now the destination is coming and the brakes they are being applied and soon it is going to stop. When it is retarding, if the retardation is this way, what you do is you convert the cases of retardation into acceleration. So this is 2 meter per second, retardation is this way, it means acceleration is in this direction, 2 meter per second square. So this is gone now. Retardation of 2 meter per second square this way means that is acceleration of 2 meter per second square in this direction, and you know very well how to find the apparent weight when the lift is accelerating down with some acceleration. That is, in this case, it is going to be once again net acceleration is downwards, so downward forces minus upward forces is equal to mass 50 into 2. So F1 is going to be 400 Newton and reading is going to be 400 by 10 is equal to 40 kg is going to be the reading. Similarly, if this lift has started from 10th floor and now the ground floor is coming and the brakes they are being applied, so that's why it is retarding in this direction with 2 meter per second square. So once again, you can convert this retardation case into an acceleration case. Retardation of 2 meter per second square in this direction means that is it has an acceleration of 2 meter per second square in this direction. So acceleration of 2 meter per second square in this direction means the free body diagram remains same. So equation is going to be F1 basic because this is accelerating in this direction. So upward forces minus downward forces. F1 minus 500 is equal to mass of the body is 50 into acceleration is 2. So F1 comes out to be 600 Newton and reading is going to be 600 by 10 is equal to 60 kg is going to the reading. So we have understood the various cases how the apparent weight changes. When the lift is accelerating up, the apparent weight increases. When the lift is accelerating down, apparent weight decreases. When the lift is moving with a constant velocity, whether it is going up or coming down, apparent weight is equal to the actual weight. If the lift is retarding in the downward direction, it means it is accelerating in the upward direction. If the lift is retarding in the upward direction, it means it is accelerating in the downward direction. So we can convert the cases of retardation into cases of acceleration and accordingly we can find the apparent weight.